All right, so let's. I hope I'm audible. So we are going to solve the week 5 assignment today. So this is week 5 assignment 5. All right. I hope the recording is on. Yes, it is recording. All right. So let's start with the first problem. Mark all the pairs of polynomials that are orthogonal with respect to the weight function. The weight function that's given to us is w of x is equal to e raised to power minus x square. And what I'm supposed to do is mark all the pairs of polynomials that are orthogonal with respect to this weight function in the interval minus infinity to infinity. The interval given is minus infinity to infinity. So what is basically the orthogonality relation? Orthogonality relation. Orthogonality relation is simply integral. So in this case, because the interval is minus infinity to infinity, so the limits are minus infinity to infinity, w of x, c1 of x, c2 of x, and dx. This is what the orthogonality relation tells you. And if this comes out to be 0, then c1x and c2x are orthogonal to each other. That's the whole idea. So now to see whether this happens or not, I will of course as usual not solve all the parts. Uh, I'll solve maybe just one or two parts. The remaining is your job. All right. So let's see. The first option is c1 of x is equal to 3x and c2 of x is equal to 4x square plus 1. So using the orthogonality relation, this is basically integral minus infinity to infinity. C1 of x is, so w of x is e raised to power minus x square. C1 of x is 3x. C2 of x is 4x square plus 1 dx. Now, under normal circumstances, this is of course integrable. You have some polynomial function. You have basically 12x cube plus 3x into e raised to power minus x square dx integration from minus infinity to infinity. This is a standard Gaussian function and there are some coefficients, polynomial coefficients. So this is a this is a well-known integral and you can solve this. But in our case, we don't even need to do that uh, for the simple reason that you take just x outside, 12x square plus 3 going from minus infinity to infinity e raised to power minus x square dx. Okay, so now look at this. The limits are going from minus infinity to infinity, but the function inside is an odd function. This is an odd function. Why? Because e raised to power minus x square is an even function. 12x square plus 3 is also an even function, but x is an odd function. So an odd function multiplied by an even function gives you an odd function. So the function inside is an odd function. And because this is an odd function and the limit is going from minus infinity to infinity, that's why we already know that this is going to give us 0. Hence, we know that in the first option, C1x and C2x are C1 and C2 are orthogonal. Therefore, this one is correct. Similarly, we go to the second one. Let's check out the second option. Second is C1 of x is equal to x plus x square plus x cube, right? And second is x minus 4x square. C2 of x is equal to x minus 4x square. Alright, so again, the same exercise, e raised to power minus x square multiplied by these two polynomials, which will give me, I'll directly multiply these two polynomials actually. So x square minus 4x cube plus x cube minus 4x power 4 plus x power 4 minus 4x power 5. So 4x cube plus x cube minus 4x power 4 plus x power 4 minus 4x power 5 dx. This is the entire equation. Also, we know that the odd powers are going to vanish away, right? So, because it's an odd function, so that integral will be divisible. So, this and this, we don't need these terms. What we need is, what eventually gets left out is e power minus x square minus 3 x raised to power 4 dx. So what we need is the integral x square e power minus x square dx minus infinity to infinity minus 3 integral x power 4 e raised to power minus x square dx. Right, so there is a method to do this. Integral e raised to power minus alpha x square dx going from minus infinity to infinity gives you square root of pi by alpha, right? A simple way, del by del alpha of this thing is equal to minus del by del alpha, by the way, yeah, with a negative sign. So that gives you what? X square, because alpha is not a variable over which we are integrating, we can take del by del alpha inside the integral. And if we do that, once we take del by del alpha inside the integral, I get x square inside the integral. E power minus alpha x square dx is equal to square root of pi into, with a negative sign outside, minus 1 by 2 alpha raised to power minus 3 by 2. And now I'll differentiate this again with respect to alpha. So minus del by del alpha into this thing gives me what? It gives me integral minus infinity to infinity x raised to power 4 with a positive sign, of course, because there's a negative sign outside already, minus alpha x square dx is equal to 1 by 2 into, because there's a negative sign again, 3 by 2 root pi alpha raised to power minus 5 by 2. Now take alpha is equal to 1. So in that case, what I get is integral x square e power minus x square dx is equal to this term with alpha equal to 1. So that gives me root pi by 2 integral x power 4 e raised to power minus x square dx is equal to 3 root pi by 4. This is the second term. So yeah, these are the two values of the integrals that we get. The question here is, this is it, this and this. So root pi by 2 minus minus 9 root pi by 4 is equal to minus 7 root pi by 4, which is of course not equal to 0. Therefore, the point is that C1 and C2 are not orthogonal for the second part. So this one's wrong. We'll not mark this pair basically. So yeah, that's your question number one. I hope this is clear. There shouldn't be any doubt here. Let's go to the next one. Alright, now this is the second problem. Consider the polynomials. These are the two polynomials given, C1 and C2. They're asking that we're supposed to check whether they are orthogonal to each other with respect to the weight function w of x equal to 1 in the interval 1 to 2. Then make a linear transformation y is equal to ax plus b so that the transformed polynomials are orthogonal in the standard interval minus 1 to 1. What are the transformed polynomials? Okay, so first we have to check whether they're orthogonal with respect to the weight function w of x equal to 1 inside the interval 1 to 2. This can be mapped to minus 1 to 1. We know that any interval a to b can be mapped from a to b to minus 1 to 1. But that's not the first step. We're supposed to check directly whether these polynomials are orthogonal in the given interval. So let's do that. Uh, Weight is 1. Okay, so let's go about checking directly. Integral 9 minus 12x plus 4x square multiplied by 2568 minus 7200x. Sorry, yeah, 7200x plus 7440x square minus 3360x cube plus 560 x power 4. Okay, so these are just some huge numbers, and maybe we'll just go about doing brute force calculation, but I'll use a calculator for this. The number calculation is a little bit tedious. So 9 into 2568. 9 into 2568 gives me some 23,112. 9 into 7,200 gives me minus 64,800 x plus 1440 into 9. So plus 66,960 x square minus 30,240 x cube plus 5040 x power 4. This is just These are just terms corresponding to the constant number. minus of 12x. So 2568 into 12, 3816 x minus 86 400 x square, and 440 into 12 plus 89 to 80 x cube minus 3360 into 12 minus 4320 x power 4 plus 560 into 12 6720 x power 5, and this is the minus sign. All right. Plus 568 into 4, 10 272 x square minus 7200 into 4, 28 800 x cube x power 4, 13 440 x power 5. Final term is 516 into 4, 2240 x power 6. So therefore, the total is like 223112, 64 800. This is minus, and 3816 is also minus. So 3816, yes, two terms. So this is minus 95 616x. Maybe let's try plus 66960 plus, this is plus and this is also plus, 86 400. So we're dealing with x square right now, yes. So this is also plus 10 to 72, 163 632, 163 632 x square. Hmm. Minus 30 to 40. We are looking at the x cube terms, plus 89 to 80 oh sorry, I made a mistake, 30 to 40 plus 89 to 80 plus 28 800. So this is minus 148320 x cube. Here this is 5040 plus, minus minus becomes plus, plus 4320 x power 4 plus 29 sin 60, 29 sin 60 x power 4. This is plus 75 120 x raised to 4. 75 120 x power 4. Um, this is okay. Now x power 5 is here. With a negative sign, 6720 plus, because there's a negative sign both, 1 3. Can't take a single backspace, is it? Okay. What is it? 6720. 6720 plus x power 5 is 13440. So this is minus 20160 x power 5. 20160 x power 5. And yeah, the last one is just plus 2240 x power 6. All right, so this huge term, just integrating this. So this is equal to 23112 x 122 minus 95616 x squared by 2 plus 163632 x cubed by 3 minus 148320 x power 4 by 4 plus 75120 x power 5 5 minus 20 60 x power 6 by 6 plus 2240 x power 7 7 by 7. Hmm. Okay, so this term just stays the same. 23112. 2 minus 1 is 1 minus 95616 by 2. Yeah, so I'll have to perform the divisions also again. 95616 divided by 2 is what? So 47808. 47808 into x squared is there 3 into 3 because 4 minus 1, right? X square, when I put the limits 1 to 2, there is 2 square minus 1 square, which is 4 minus 1, which is 3. So this basically gives me 143424 plus 163632 divided by 3. Great. Multiplied by, again, x cube, 2 cube minus 1 cube. So it's 8 minus 1, which is 7. So plus 381808 minus 148320 divided by 4 multiplied by 2 power 4, which is 16 minus 1, 15. So minus 556200 plus 75120 divided by 5 multiplied by 2 power 5, which is 32 minus 1 is 31. 465744 minus first term, second term, third term, fourth term, fifth term. So 20160 divided by 6 multiplied by 2 power 6 is 64 minus 163. Sorry, 60 divided by 6, 63 minus 211680 plus 2240 divided by 7 multiplied by 128 127 plus 40640. Whew, that's the whole term. 23112 minus 143424 43424 plus 381808 minus 556200 plus 465744 minus 211680 plus 4640, and this number is exactly 0. After this huge calculation, what we arrive at is that C1 and C2 are orthogonal to each other in the interval 1 to 2 with the weight function wx equal to 1. Now make a linear transformation y equal to ax plus b so that the transformed polynomials are orthogonal in the standard interval minus 1 to 1. Okay, so let's do this. Y is equal to ax plus b. What I want is when so the limits for x is x equal to 1 to x equal to 2. What I want is in this interval range y should go from minus 1 to 1, so that when x is equal to 1, y is equal to minus 1. X is equal to 1 should imply that y equal to minus 1. X equal to 2 should imply y is equal to 1. Because the new limit has to be from minus 1 to 1, the old limit is from 1 to 2. So let's do it. Uh, y equal to minus 1 when x is equal to 1. So y equal to minus 1 is a plus b. Next is y equal to 1 when x is equal to 2. So 2a plus b. Subtract the second equation from the first. I get a is equal to 2. And once I do this, I get b is equal to minus 3. So that y comes out to be 2x minus 3. Therefore, x is equal to y plus 3 divided by 2. Now, use this value of x in all the polynomials, c1 and c2 both. So c1 of x, actually, like at this point, again, I have almost made the entire problem clear, but this is just about actually working this out. So you put x is equal to y plus 3 in these polynomials, and whatever the answer you get is the correct answer. Yeah, so maybe I shouldn't show the entire problem. I've given you the major ideas or insights where you can progress, but substitute this and get the answer. That's your method to solve. I hope there is no confusion in the method. Mhm. If there is, for those who are watching this online, if you find any questions or doubts, you can just post in the comments. Let's move on to the third problem. All right, so I just wrote down the term. So what's the question? The question is, suppose we construct a sequence of functions of the form Cn is equal to this, uh, which all satisfy the orthogonality relation. With the standard orthogonality relation, they all satisfy. Mark the correct statements. The correct statements which they are asking us to mark is the function Cn of x are unaffected if we scale w of x by an arbitrary positive factor, but the orthogonality property may be affected if we scale s of x by some factor. So basically, the idea is that we are scaling both w of x and s of x, and we want to see what is the change in the function c of x and the orthogonality relation. Do either of them or both of them change? That's what, or neither of them. We want to see whether there is any change at all. Okay, so this is my Cn of x. The orthogonality relation that we are looking for is something of this form. We want to see whether there is any change in this or this. Okay, the orthogonality property is that this is to be equal to 0. So eventually, even after scaling, if we are finding this is equal to 0, then the orthogonality property is unaffected. Even after scaling, if we see that Cn of x maintains its nature, it remains the same, then Cn of x is also unchanged. So this is what we want to see. So first scale w of x becomes some alpha w of x. Let's call this some w prime of x. Similarly, s of x scales by some beta s of x is equal to some s prime of x. Therefore, Cn of x 1 divided by alpha w of x. This is the new Cn, right? dn by dxn s power n, which is beta raised to power n s raised to power n alpha w. These are the functions that emerge. Now, because beta and alpha are constants, so I can just take them outside. So this becomes beta raised to n divided by w dn by dxn. The alphas get cancelled off. The alpha outside and the alpha inside, once it comes out, gets cancelled. So s power n w. This is which is basically beta raised to n Cn of x. By the way, this is tilde. Cn of x tilde is some beta raised to n Cn of x. And beta is the scaling factor corresponding to s of x. So scaling w does not affect Cn. Scaling s does. And what about the orthogonality relation? So integral Cn x power p w, so w dx. So in this case, it's beta raised to n, which comes out integral Cn x raised to p w. Okay, so w also is scaled now, right? W is alpha into w, which I can take common outside. Alpha w dx. So these are constants outside, but the inner thing still goes to zero. So the orthogonality relation is not affected because of scaling, but Cn value will be affected. So that's your answer. Accordingly, you can choose any of the options. Cn may change if we scale W by certain positive factors. It's about S, not W. So option 4 seems to be the correct one. Cn is unaffected if we scale W by arbitrary positive factor. So W scaling does not affect Cn, that's what we saw. And orthogonality property is unaffected if we scale S by some factor. We saw that both can be scaled, but still orthogonality property still remains the same. So yeah, the fourth one seems to be the correct option. Let's move on to the next question. So yeah, we have seen that the orthogonal polynomial Cn of x satisfy a three-term recurrence relation in which the coefficients alpha n, beta n, and gamma n appear. If for a sequence of such polynomials, we are given that Cn of 0 at basically Cn at x equal to 0 is 1, which of the following relations must hold? So this is one question. What is the three-term recurrence relation? What is this three-term recurrence relation? It is basically Cn plus 1 x minus of x. There is some constant alpha n Cn of x, and this is equal to beta n Cn of x plus gamma n Cn minus 1 of x. This is a three-term reconciliation because it's a relation between Cn plus 1, Cn, and Cn minus 1. That's why it's a three-term reconciliation. And it's given that Cn of 0 is equal to 1, which implies that because n is a general number, it's not like here when you say Cn is equal to 0, Cn of 0 is equal to 1, it does not mean that only this Cn is 1 and Cn plus 1 is something else. No, here they're trying to tell us about some general n. So C of any n at x equal to 0 gives you 1. So that is why, of course, Cn plus 1, Cn minus 1, all of them are 1. So therefore, 1 is equal to minus, and x is equal to 0, by the way. So x, because x equal to 0, the second term does not matter. So therefore, 1 is equal to beta n Cn of 0, which is 1, plus gamma n Cn minus 1, gamma n. Okay, so the fourth question is done. Now we move to the fifth question. Um, Consider the function f of fn of x is equal to this term. So we've seen this function in lectures. Cn of x are a sequence of orthogonal polynomials with weight function w, and Sx is the standard factor that we have seen. Let p and n take non-negative integer values. Okay, so p n are some non-negative integer values, and they're asking us to mark all the statements that are correct. Uh, okay, so this is actually something very uh, not a complicated thing because we've already seen in the lectures that fn of x are indeed sequence of polynomials of degree n. Sequence of, sorry, my bad. What I meant to say is they are sequence of orthogonal polynomials of degree n. That's an important part. So because fn of x are sequence of ortho, so the derivation of this, by the way, is given in the lectures. So you can just check that out. I don't think I need to derive it here again. So, and it's a very standard derivation. It gives some three-term recurrence relation, and you put that reconciliation in the orthogonality relation, and you see that um, for polynomials less than the for basically polynomials of order less than n, function f of n is orthogonal. You see that there is an orthogonality relation being satisfied. So that's why the derivation is basically given. So once you have the derivation in mind, once you know that for a fact that fn of x are also a sequence of orthogonal polynomials of degree n, then you know something more because they're orthogonal polynomials. sorry, we know that fn of x, x raised to p, w of x of course, dx is equal to 0 for all p less than n. See, x power p's are not a sequence of orthogonal polynomials, but fn of x is of order n, and where n is a number greater than p. So we know that for x power p where p is less than n, fn of x has to be orthogonal to x power p. This we know for a fact because fn of x are series of sequence of orthogonal polynomials. They satisfy this basic condition. So this is correct in that sense. But for p greater than n, x power p being orthogonal to all numbers less than p is not a true statement. That's what I said. X power p are not a sequence of orthogonal polynomials. Fn of x is a sequence of orthogonal polynomials. So for p greater than n, this statement need not hold true. For p less than n, it holds true. For p greater than n, it need not hold true. I hope the idea is clear here. Whereas on the other hand, for fn of x, so basically for third and fourth option, that you can give it a thought. What happens in that case for p less than n and for p greater than n? Are both these statements true, or again, even in this case, p less than n only has to be true? You should give this a thought. This is something I'll give you as a homework. Basically, that's anyway, it's your job to solve this assignment. So, yes, question 5 is done. Let's move on to question 6. From here, we are talking about all these polynomials, Hermite polynomials and Legendre polynomials. Okay, so we are at problem 6. So the question is, we have to use the generating function to study the lowest powers of the Hermite polynomials, and we have to mark all the correct answers. Okay, so the generating function basically g of x is the generating function, and g of x basically is e raised to power 2xt minus t square, and we know that the nth derivative, um, and then t equal to 0 is equal to hm of x. Yes, so this is what we get. This is what the function, this is what the relation is with the generating function. So I have to use this generating function to study the lowest powers of the Hermite polynomial. E raised to power 2xt minus t square, which is a generating function, is actually equal to this whole series. N goes from 0 to infinity, t raised to 2n divided by, so here this is also a series going from 0 to infinity for hn of x. Instead of n, I'm putting in 2n. And the left hand side is also, because it's an exponential function, simply 2xt minus t square, um, basically it's x power n divided by n factorial, where n goes from 0 to infinity, and this is equal to 0 to infinity t raised to 2n hn of x divided by 2n factorial. Here I forgot to put an h2n, my bad. H2n of x is what I find here, right? So now, mm, so 1 by n factorial, this is very small, let me make this larger. So sum over, that's the outermost thing, n equals 0 to infinity, 1 by n factorial is also outside. Um, Now n goes from 0 to infinity. So assuming that n is some large number, we can do a binomial expansion here, uh, for this individual terms, where there is some r equal to 0 to n, 2xt raised to power r and minus t square raised to power n minus r. This is what we're supposed to ideally get. And also there will be a selection term. So NCR. So we're just doing, basically what we're doing here is, uh, this is the generating function. I'm writing down the sequence here, and the generating function I'm breaking it into its Taylor or Maclaurin series, whatever you call it. I'm breaking it into its Taylor series expansion, where it's this entire summation, which is equal to the same right hand side. Now this summation, each individual term here, this 2xt minus t square raised to n, I'm doing a binomial expansion on that term. So that's why each term with whatever n there is, each term is going to give me an expansion of this form. So that's why I get another summation here. It goes from r equal to 0 to n. So if n equal to 0, then there is no term. N equal to 1, there are a couple of terms, etc., etc. Things like that. So that summation is NCR 2xt raised to r minus t square raised to n minus r. Okay. And this is equal to n equal to 0 to infinity t raised to 2n. Okay, again, I have made a mistake here, of course. Uh, oh, no, 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 I have not. I have not. No, no, this is fine. T raised to 2n h 2n of x divided by 2n factorial. Now, mm, So t power n in the full limit minus say minus infinity or something like that. Uh, T power n are orthogonal to each other. So therefore, if left hand side has a term t raised to 2n, the right hand side has a term with the same coefficient. You can directly match out coefficients. That's what I intend to say here. That basically because t power n are orthogonal polynomials, so that is why you can just read out the coefficients directly, right? I can't. So for t square on the left hand side and for t square on the right hand side, I can directly read out the coefficients. I don't need to consider any other power of t to read out the coefficient of t square. Yeah, so let me erase this. All I meant is directly read out coefficient of t raised to 2n. What is the coefficient? For that on the left hand side, I need to put r equal to 0. If I put r equal to 0, so that gives me minus of t power 2n. Because it's 2n, r equal to 0, so it's 2n, so the minus sign goes away. It becomes t raised to power 2n. Let's write it down. N equal to 0 to infinity 1 by n factorial, and I just want the r equal to 0's coefficient, so which is nc0 to xt raised to 0 t raised to the power of 2n, which is equal to n equal to 0 to infinity t raised to 2n h2n of x divided by 2n factorial. Yes. So therefore, what I'm getting here is h2n maybe I think I made a mistake here. only one t raised to power 2n, but I'm actually slightly confused what's happening here. Sorry for that. N equal to 0 to infinity. Uh, 1 by n factorial sum over r equal to 0 to n ncr to x raised to r t raised to r to minus t square raised to n into square minus r. The minus sign isn't something to be bothered about. N can be odd or even, we don't know. So that minus 1 raised to the power of n minus r is okay outside. But ncr mm, this method after even though worked out, but now I think that basically I'm not very convinced how this works out. So I would not want to. So here basically there are two summations. On the right hand side, there is n equal to 0 to infinity. Basically, I'll tell you what my confusion is. h2n of x divided by 2n factorial. Maybe it's not clicking me right now, but uh, here n is going from 0 to infinity. It can take any value. Uh, okay. On the other hand, in this expression, there is a sum over r first in the first place, and there is a sum over n as well. So the confusion that I have is uh, I have to compare powers of t, and because there are two summations here, I would end up getting powers of t in two manners, in two ways, from r also, the range of r as well, and from the range of n. So For n equal to 6, I will have t raised to power 12 corresponding to r is equal to 0. For n is equal to 7 as well, I will have t raised to power 12 with r is equal to 2. So the point being that there are these kinds of terms here on the left hand side. On the right hand side, we can match these powers. So this is something I'm not very convinced with. So let's try to get an answer from some other method. Uh, H2n. I don't know whether this will work out, but let's just try. D2n by dtn. D2n by dt2n g of x. So d by dt of g of x gives you what? Give you 2xt minus t square e raised to power 2xt. Sorry. Then I'll go for the second derivative, g of x. One term will simply be derivative of this, which will give me 2x minus 2t e raised to power 2xt minus t square plus 2xt minus t square whole square e raised to power 2xt t square at t equal to 0. T equal to 0. So this gives me what? No, no, this will also be 2x minus 2t. This will be like further derivative. I'm sorry, I'm making some mistakes. This will be another derivative which gives me minus 2 minus 2 plus. So here I'm not substituted anything. I'm just differentiating this. What I end up getting is 2x minus 2t multiplied by, I don't get this term outside, I get the derivative again, which just squares this up, which gives me 2x minus 2t the whole square. And there has to also be minus 2 here. So this becomes plus 4. This is still minus 2. My bad, I'm making some very silly mistake. I'm sorry. Mm, There won't be minus 2 here and here. It will just be 2x minus 2t because I'm taking a derivative of this function. Alright, so it will be just be 2x minus 2t the whole square, and here it will be minus 2. So basically for the second derivative, I have some constant term as well. Now if I go for the third derivative, d3g by dt square dt cube. So here, because of the constant term, I will get 2x minus 2t into minus 2 e raised to power 2x t square plus here there will be some derivative of the function and like of the exponential and the polynomial both. But then when you go for d4g by dt4, what you end up getting is again this is differentiated minus 2 into minus 2 e raised to power 2xt minus t square. And then there are a lot of other terms. You'll differentiate this and keep this constant, etc. But the point being that at every even uh, power of the derivative, we are ending up getting one x power 0 term, at least one x power 0 term. At t equal to 0, this will become just 1, and we'll be landing up with this coefficient. So what this coefficient is exactly is actually 2xt minus t square. There might be some other terms as well. So my point being that there is at least an x power 0 term which always exists. So the lowest power of h2n is x power 0. But for the other options, so I'm sorry, but I'm not very sure how to solve the other part right now. So I'll just look this up properly and get back. So the method with which I had thought of does not seem to be very accurate. Like I have doubts in that method. So I'll just let it be for now and solve the other problems and get back on this problem in the next week. Just giving it a thought again. Um, what I'd also known is that you directly compare the coefficients of t raised to power 2n, which is a fine proposition, but given that on the left hand side there are two summations involved. Mm, I'm still not able to figure this out completely. So without wasting any more time, I'll skip this problem and move on to the next one. Um, I'm sorry about this. I'll get back with this problem in the next lecture. Okay, so now the next question is compute this integral. IMMN is equal to integral minus infinity to infinity x hn of x hm of x e raised to power minus x square dx. So I of 10 comma 11, 8 comma 10, etc. These are what you're supposed to calculate. All right, where basically 10 comma 11 is basically the value of n and m and n respectively. Okay, so firstly what we want to eliminate is x into hn of x or hm of x, whatever. So for that, what we'll do is we'll use a recurrence relation. The I'm sorry, the recurrence relation corresponding to Hermite polynomials h of n plus 1 x is equal to 2x h n of x minus 2n h n minus 1 x. So this is my recurrence relation for Hermite polynomials. Um, x h n of x is right here. So that is why the substitution would be that x h n of x is simply equal to h n plus 1 of x plus 2n h n minus 1 x divided by 2. So therefore, I of m comma n is equal to, I'll split this into two integrals, minus infinity to infinity, 1 by 2 h of n plus 1 x h n of x e raised to power minus x square dx plus n integral minus infinity to infinity h of n minus 1 x h n x e raised to power minus x square dx. Okay, so looking at this, one thing you can say for sure is that, by the way, these normalization relations are also very standard. We know uh, what we get for n comma m. Basically, integral h of m x h of n x e raised to power minus x square dx is simply 2 raised to power n into n factorial square root of pi delta mn, of course. If m is not equal to n, then this becomes 0. So in this case, at least one thing we are sure of is that if n plus 1 and m are not equal, or n minus 1 and m are not equal, basically the two integers should be at just difference of 1 with respect to each other. If that's not the case, then both of these integrals will turn out to be 0 because they become basically normalization orthogonality relation, and you get a 0 because there is no delta mn. So if the difference between m and n is not of just 1, in that case, uh, imn is going to be 0. This is what we can for sure say. So just two options right here. We off the bat you can mark I 10 comma 12 is going to be 0 because m and n. M is 10, N is 12. The difference is 2, not 1. Because the difference is of 2, either of these relation, this and this, both will give 0. That's why I 10, 12 is off the bat 0. I 8, 10 is also 0. But they have given some value. So this is an incorrect option. So it is two options right here you can check out. The other options, you can directly use this expression and get the answer. So this is a pretty straightforward problem, solvable. Once it clicks to you that you can use the recurrence relation here. Once that is done, this is a straightforward problem. All right. So now we're moving on to Legendre polynomials. Using the recurrence relation for Legendre polynomials, work out a general expression for P of 2n of 0 and mark all the correct statements. Okay, so what we have to work out is P2n of 0. The recurrence relation for Legendre polynomials is P of n plus 1 x is equal to x alpha n Pn of x plus gamma n P of n minus 1 x. So this is a three-term recurrence relation for Pn's. Now what I want to do is, firstly, I want to calculate for sorry, P0 of x. So P0 is just a constant term which is 1. So P0 of 0 also is equal to 1. Now putting x equal to 0 in this recurrence relation, what I get is Pn plus 1. By the way, gamma n also has some form, right? Gamma n is minus n divided by n plus 1. Right. So Pn plus 1 of 0 is equal to the second term becomes 0. And what I have is minus n divided by n plus 1 P of n minus 1 0. This is the relation we end up with. So putting in x equal to 0 here. Yes. So P of 0 is 1. So I can directly go to P of n I put at 1. N is equal to 1, which gives me P of P2 of 0 is equal to minus 1 divided by 2 P of 0. So P2 of 0 is equal to minus half. P n equal to 2, P3 of 0 is equal to minus 2 by 3 into P1 of 0. But I just need P2n, right? So I'll just not use this. I'll directly use n equal to 2. Sorry, n equal to 3 directly. N equal to 3. That gives me P4 of 0 is equal to minus n is 3. So minus 3 by 4 into minus 1 by 2 into P0. So what I can do is, firstly it's minus 1 raised to the power of n is 3, n is 1. No, so that law is given. No, no, no. N that I used here, I can put up some general relation. Basically, that's what I'm trying to do. I'm trying to think of a general relation with respect to minus 1. Acha, right. So this is uh, P2n where n is equal to 2. This will simply be minus 1 is for n, I think. When I'm trying to write P2n is equal to, this is just simply minus 1 raised to power n. Because for P2, it's going to be a negative sign. P4 is going to be positive. Okay, so this is done. Minus 1 has been sorted out. Um, 2n minus 1 to 2n minus 3 up to 1 divided by 2n 2n minus 2 up to last number would be 2 into P0. This is the relation you end up with. Okay, so the general expression is this. Now what we want is, say for P10, what is P10? For P10, basically put n equal to 5. N equal to 5. So in that case, this is minus 1 raised to power 5, which has a negative sign. 9 into 7 into 5 into 3 divided by n is 5, right? So 10 into 8 into 6 into 4 into 2. P0, which is 1. Minus 1. Yeah, this is basically the answer. Um, maybe I should. Right, so what I have is 63 in the numerator divided by 4 to the 8. 8 is a 64. 64 into 4, 256. That's my P10, which is the answer here. So now for similarly, I can do it for odd P's as well. Here it was P2n. I can work out a statement for P2n plus 1 as well by doing exactly this process, exactly this procedure. But here instead of n being equal to 1, I'll be substituting n being equal to 2 or something like that. I'll start with something else. If n is 2, so I start with P3, P3 here and P1 here. What is P1? So that P1 of 0 at least I can know. Uh, the lectures, there is some relation, right? For P1, it would be 1 by 2 into n factorial is 1 d by dx of x square minus 1 at x equal to 0. is equal to 1 by 2 2x at x equal to 0 is equal to 0. So P1 of 0 is equal to 0. So then accordingly your recurrence relations for odd p's are going to be 0, and that's what you end up getting. I hope basically you can just check it out what happens. You can use exactly a similar procedure and check out what happens for P11 and other such terms, P11 and P13. Using this, you can find even P12 using this procedure itself. So all of that is doable. So that's why I'll move on to the next question now. Just exit it. Okay, sorry. So the question is use the Rodriguez formula to study the lowest power and the corresponding coefficient of Legendre polynomials and mark all the correct answers. So that's your question. So what is the Rodriguez formula for Legendre polynomials say? The En of x, this is the basic general Rodriguez formula, 1 raised to power 2, 1 upon 2 raised to power n into n factorial multiplied by dn by dxn x square minus 1 raised to power n. Right, this is the nth derivative of x square minus 1 power n, and there is some normalization coefficients in front of it. So this is your Rodriguez formula. Okay, so now when I have this, um, okay, so what I can do is I can again do a binomial expansion for the inside. Firstly, let's do this. P2n of x has to be 1 divided by 2 raised to power 2n into 2n factorial d2n by dx power 2n x square minus 1 to power 2n. This is my p2n. What I want is the coefficient of firstly the lowest power, the coefficient, etc. For p2n, let me do it for p2n plus 1. It's your job. Okay, so 4 raised to n, 2n factorial, d power 2n by dx power 2n, and we'll do binomial expansion. So 2n c r x power 2 to n minus r minus 1 raised to r. And what I'll do is this is summation r equal to 0 to, okay, this is 2n minus r. From r equal to 0 to 2n, this is the summation. Yes. So now the question is the lowest power of p2n of x is x raised to 0. Um, that being the question, that at least, so here if you see x square, um, the expansion will basically give you all the powers of x in multiples of 2, of course, starting from x raised to 0 till x raised to 4n. For r equal to 0, it will be x raised to 4n. So I will have all these powers. Uh, and you take for r equal to say n, when r is equal to n, I have some x raised to 2n and some coefficient here. You take nth derivative or 2nth derivative of this, and you will end up with some x raised to 0, which is a definite possibility here, which is definitely going to happen here. 1 by 4 raised to power n into 2n factorial. And what we are doing is we are putting r is equal to n. So minus 1 raised to n. I'm taking this minus 1 outside. Um, 2n c n. There is also the derivative though. So we have to see what the derivative gives. The term is going to be r equal to n. So this is x raised to power 2n. And I keep on differentiating it 2n number of times. So it's going to be 2n, 2n minus 1, dot, 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 up till 1. Oh, so it is going to be 2n factorial basically. This is simply 2n factorial, and that gets cancelled out. So minus 1 raised to power n divided by 4 raised to power n, 2n factorial divided by n factorial into n factorial. Okay, so this is exactly the answer that I am getting. Minus 1 raised to power n, 2n factorial upon 2 raised to power 2n, which is 4 raised to power n, into n factorial square. Exactly. So this is what we end up getting when I substitute r is equal to n. So that's what you're supposed to do. We'll take this we'll do the binomial expansion. We'll put r is equal to n inside of here, and then take the derivative to n number of times, so that I'll be able to get an x power 0. The same thing would not have happened for some odd power. That would not have been possible. So yeah, anyway, the point being that this is what you get, and you're supposed to do a similar thing for p2n plus 1 and get its coefficient. So same thing, put it in here, do the binomial expansion, you will get coefficients. You have to see what's the lowest power that you are going to get. So here, from r equal to 0 to n, there are 2n terms, but initial n terms are going to get cancelled. They are going to become 0 because of the derivative, or n minus 1 terms, whatever. But because of the derivative, they will become 0. So similarly, you have to check for p2n plus 1 as well. How many terms are going to become 0 and which is the lowest power which will survive. And that's what will give you the lowest power and the coefficient corresponding to it also. So that's what you're supposed to do in this problem using the Rodriguez formula. I hope this one's clear. Uh, this is just binomial expansion. Use the Rodriguez formula to work out the coefficient Cn of the highest power of Pn of x, which may be written in this manner. Okay, okay, let's do this. Again, a very similar problem, I would say. Okay, Rodriguez formula to work out the coefficient Cn. So Pn they're writing as En of x. They're writing it as some Cn x raised to n. This is how they're writing it. Um, all right. So what do I do here? Um, Again, same Rodriguez formula as they've already mentioned, which is what? Which is 1 divided by 2 raised to power n into n factorial dn divided by dx raised to n x square minus 1 raised to n. So coefficient corresponding to look at it for charging, sorry. Corresponding to x power n. Okay, so let's do this. This is equal to 1 upon 2 raised to power n into n factorial dn by dx raised to n. And again, the binomial expansion, like we did in the last problem, it will be sum over r equal to 0 to n x square n minus r minus 1 raised to r. I want the highest coefficient, so that will occur for r equal to 0 only. So it is 1 divided by 2 raised to n into n factorial by dxn of um, forgot the NCR part, right? NCR. So now r equal to 0, so it's basically NC0, which is just 1 into x raised to power 2n minus, yeah. So this is 1 divided by 2 raised to power n into n factorial and n derivatives. So that gives me 2n into 2n minus 1 into 2n minus 2, so on up to n plus 1. So this is almost like 2n factorial divided by n factorial, and this is the prefactor upon 2 raised to n into n factorial. So basically equal to 2n factorial divided by 2 raised to n into n factorial square is my coefficient. This is Cn. Let's see what we get. C3. Let's try C3. C3 is equal to 6 factorial divided by 2 raised to 3, which is 8 into 3 factorial into 3 factorial is equal to 6 into 5 into 4 to 3 factorial divided by 8 into 3 factorial into 3 into 2. So I just cancel out 3 factorial, 3 factorial, 2, 2, 2 is equal to 5 by 2. That's the correct answer. And similarly, check the other options, and whatever you get is your answer. So that brings us to the end of this assignment. I have not solved one problem in this assignment, which I'm sorry to say, but I got slightly confused as to how to solve it, how to approach it. The method that I've used is not satisfactory to me. So maybe the next time I will solve it and present it, right? So this assignment one problem is pending. Otherwise, we've solved all the problems. We've got a good enough idea, so you can proceed by yourself. That's it. And okay, see you guys next time. Thanks. Bye.